teaches using partial quotients to solve division problems. In grade 4, Unit 6, Lesson 14, Illustrative Mathematics takes the transition from multiplication to division strategies. In this lesson, they're using area situations to get into dividing. We're thinking about area, just like students did in 3rd grade, as one side times the length of a missing side will give us the area. Or in division, when we know the area, we can divide by the side length that we know, and the quotient is going to be the missing side length. This is connecting to the area model that students used earlier in Unit 6 to multiply a single digit times a multi-digit number. In the teacher notes for Lesson 14, this is one situation that it highlights teachers should be looking for students to use. You can see here that the student thought about a fact that they knew 7 times 10 would give them an area of 70 square tiles. And then I can fit multiple sets of 7 times 10 in that rectangle. And then I have 49 square tiles left that I need to figure out the missing side length for. And 7 times 7 equals 49. Then when I add up all the partial quotients, those partial side lengths for the missing side, I get 27. So that means that 189 divided by 7 is equal to 27. So the length is 27 tiles. In Lesson 17, students move on from using base 10 blocks and continuing to talk about that area model for division, and they move on to more base 10 work that's a little more abstract. They start to shift to partial quotients. So when I was dividing by base 10, I would think, well, how can I divide that 400 by 5? How can I divide the 10s by 5s? And how can I divide my 1s by 5? So this problem allows me to do that, although if I was using base 10 blocks, it's a little tricky because I can't just put one whole 100 in each of those groups. I have to break them up. So for this one, you can see here that on the left side, the student is dividing each part by place value unit by 5. 400 divided by 5 is 80. 60 divided by 5 is 12. And 465 divided by 5, therefore, equals 93. I added up the partial quotients to get my final quotient. Over here, this probably looks like the traditional algorithm that we learned, or that you were taught. Here, the student is dividing 400 by 5. They say that 80 times 5 is equal to 400, which leaves me with 65 left. Then I can think that 65 divided by 5, if I think 12 times 5 is 60, I have 5 left, and 5 divided by 5 is 1. So then when I add up these partial quotients, my quotient is 93. Very similar to the long division model you probably know, the way they were writing their thinking to the side and these partial quotients at the top might be slightly different. You'll also notice that this really requires some really precise place value language in order to make sense of it. So we really need to be conscious of not saying anymore, well, I can't divide 4 by 5, I have to divide 46. Really what we're asking is, can I divide 400 by 5? Yes, we can. So we want to make sure that we're using that place value language. Let's take a look at what they do next. Before we look at the next lesson, Lesson 18 in Unit 6, we're going to take a look and practice this problem together, using partial quotients, but not by place value unit, by friendly facts. So if we again think about this division expression in related to area, we know that the 4 is the length of one side, And we know that 132 is the area of this rectangle. So now let's think about what it would look like to divide using friendly facts. So when I divide by 4 and I look at the number 132, as an adult, the first thing that comes to my mind is 4 times 30 is equal to 120. So I'm going to put a 30 up here because that was my first partial quotient. When I subtract, I have 12 left to divide by 4. And again, I think pretty quickly, 4 times 3 is equal to 12. And that gives me 0 remainder. So up here, my partial quotients add up to my quotient of 33. So let's think about what this might look like for a partial quotient model if I wasn't quite as quick on my feet with those facts. Over here, I have the area model, and I'm going to think about dividing 132 by 4, but I'm really going to think about the area. When I think up here, I know 4 times 10 is 40. I also know, if I keep track down here, 132 minus 40, that's going to give me 92. I could do that over here also. I could put my, whoops, not my 40, my 10 up here. And I'm going to get 40, and when I subtract, I'll see I have 92 left. So 92 in either one of these situations is telling me the area of the remaining part of my rectangle. So if I'm sticking with my, I know my times 10, I could do 4 times 10 again and get another 40. So I'm going to take away another 40 over here to keep track of my area. Or I could think over here times 10 again. That gives me 50. Or sorry, 40, which gives me 52. And once again, I can put another 10 in here, which will give me 40. So if I go over here, I took another 40 out of that area, which left me with 12. And I could do the same thing over here, do another 10 times 4, 40, and that gives me 12. If I go back up to the area, I know that this part is 12. So what number, 4 times what number, gives me 12? 3. Here, I know if I get rid of that 12, I'm done with the area over there. And if I think 3 times 4 is 12, that also lets me know I finished over here. So notice, when I add up these partial quotients or these partial quotients, I'm going to get the same quotient as I did over there. It might be a little less efficient, but it is more accessible for our students who are a little intimidated or maybe not as fluent with their facts for multiplication. In grade 4, Unit 6, Lesson 18, they take a big jump and they start to look at partial quotients and they start to discuss and think flexibly about how students can solve division problems. This slide is near the end of this lesson, and it asks students to pick one of the 4 partial solutions that you see here on the slide and finish the thinking for the student that left it undone. Okay, take a minute to take this in. I went ahead and finished the thinking for each student's work. We're going to talk through all 4. In A, This looks pretty similar to what you might have done if you're familiar with the standard algorithm. They did include that partial quotient multiplication thinking on the side, and they recorded each step not as a 1 or a 9, but a 1,000, 90, and an 8. Again, here you're seeing that we're really honoring the place value for each number and not shortening anything to 3 divided by 3. This is 3,294 divided by 3, and the first partial quotient, or first chunk of that area we're thinking about, is 3,000. In B, over here, this is a slightly less efficient approach, but again, uses facts that students might be familiar with. Over here, we got to a 9 times, and it might not have come to students right away. You'll notice over here, we stuck to some more friendly facts to start with. We knew 3 times 400 was 1,200. Then we could take another 1,200 out. When we got to 894, we couldn't do 1,200 anymore, so instead we switched over to 3 times 200, which gave us 600. Then we couldn't do 600 again, so we needed a new fact. This time we decided to try 3 times 80, which is 240. I took the 54 that were left, and I thought about 3 times 10 and 3 times 8 could take away those parts. These are all my partial quotients up here. When I add them up, I get 1,098, which is the same quotient as this method. Now let's take a look at C. So in C, we're also doing partial quotients, but we're thinking about them as division instead of multiplication over here. I'm thinking that the student saw 3,000 as an easy part because I know 5 times 6 is 30. I could also know that 5 times 600 is 3,000. And we know that 600 is pretty easy when we divide it by 3 because 600 divided by 3 is 200. So 5 times of 600 divided by 3 is 200, as shown here. Then we see the next big chunk we could do is 270. We knew our 9 times tables, or we maybe knew those tricks for the 9s. That left me with 24. And when I think 24 divided by 3, I got 8. And again, if I add up all of these partial quotients, I get to 1,098. So these methods, I think, make it accessible for students if we don't know our facts or we're intimidated by those big numbers. This one is a great extension that I never would have thought of before looking at this lesson. In this problem, the student thought, well, 3,294 is pretty close to a really easy number to divide by 3. It only needs 6 more to be 3,300. I can divide that by 3 really easily in my head. So what they did is they divided 3,300 by 3 and got 1,100. I added 6 to that 3,294 to get to this. So I'm going to divide 6 by 3, which gives me 2, and subtract those 2 from my 1,100 to get me 1,098. This kind of reminds me of the compensation method when we think about making an easier number to subtract. We can add to it and then take it back at the end. So think about the work that's happening here in 5th grade, in partial quotients, in Unit 4. They only use partial quotients. Students can use place value, but it's not necessarily the way that they show it. A lot of the times they're using friendly facts. And when you're doing this with a 2-digit divisor, or a multi-digit divisor and a 2-digit dividend, it makes things a little bit interesting. So using these partial quotients can help it feel a lot more accessible.